हेलो। 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 हेलो हेलो।
Good morning, everybody. Welcome to the second day of our FDP. Today we have Biranji Narayan Rath, doctor from Silicon Institute of Technology. So I'm sure that this is going to be another very wonderful learning experience. The point why I say this is because a lot of times we keep hearing from scientists and distinguished professors of, very high stature and all. But sometimes we get paused with this idea that what can we do? We are into private engineering colleges and our funds are limited, our powers are limited, our access is limited. And we don't even get the promotions like what generally chronologically what happens. So amidst all of this, how can we still navigate through our vision mission of life and still have this passion to pursue our research is something that Narayan sir would now tell to you. So, Biranjan Narayan Rath is an academician and researcher currently serving as a senior assistant professor in the Department of Electronics Engineering at Silicon University. With over 4 years of post PhD experience and a cumulative of 15 plus years in academia, Dr. Rath specializes in control and automation, artificial intelligence, machine learning, and their applications in solving real world challenges including unmanned vehicles and active noise control. Dr. Rath earned his PhD from National Institute of Technology, NIT Rourkela, with a focus on designing robust and adaptive control algorithms for autonomous underwater vehicles. He also holds an MTech in Control and Automation from NIT Rourkela, graduating with distinction, and BTech in Applied Electronics and Instrumentation from Silicon University, Bhubaneswar. Dr. Rath has made significant contributions to government funded research, serving as principal investigator for SERV DST project on adaptive active noise regulation systems using deep learning techniques. Additionally, he has been a key contributor to the Indo Russian collaborative DST projects, focusing on innovative control and communication strategies for autonomous underwater vehicles in uncertain environments. An accomplished researcher, Dr. Rath has numerous peer reviewed articles published in reputed journals, conferences, and book chapters. His academic influence extends to guiding two PhD scholars fostering the next generation of researchers in the field of AI/ML and control systems. Dr. Rath is also a dedicated educator and mentor, having supervised several master theses and research internships. He has conducted impactful training programs in machine learning and deep learning, leveraging his experience in Python, MATLAB, and deep learning frameworks to develop hands on sessions. So, ladies and gentlemen, I would like to make a request you to make use of this opportunity to your level best in trying to understand as a fellow researcher what are the pitfalls that Narayana sir must have faced while applying for his grants and how he is able to manage his time, mentoring students, writing grants, publishing papers along with teaching load. So, I would like to now welcome sir onto the stage.
So, after all this, everything that I want to talk about is like AI-driven autonomous underwater vehicles. As I'm seeing marine technology with robot and adaptive control. So basically, my objective over here is to provide an insight regarding how to develop a robot. So when the word robot comes to the picture, it becomes very tough for our scenario, so how to design it. Okay, for example, when I joined in a Raulkela, actually I have completed my bachelor from near your college, like near your institute, like Silicon. Yeah, after completing this, then I joined masters at NIT Raulkela to get. And once I joined there, then suddenly there's a proposal like I should design uh, a robot. And to design a robot is very, it's not so easy because I belong from instruments background. I don't have any idea regarding the mechanical part of it. Okay. So I have to like take help from my seniors and others who have guided me to like to learn AutoCAD for. Like once you know the AutoCAD, then you can go with the designing part. Then you can, once the prototype is ready, then only you can implement a control algorithm. And unfortunately, the real part is that nobody's going to see the hardware. Okay, everyone's going to see the result and how your robot works. Okay, and what how your effort you have put for the designing part is no one going to no one is going to question. Okay, but the real challenge is that designing the hardware part. It's like almost my 3 years have like I've used of my PhD like in designing this hardware. Okay, why it is very tough? Because this robot is going to go underwater. A drop of water is going to like completely destroy your setup, right? So you need to be very careful when you design a robot. So the robot that we have designed is what is called autonomous underwater vehicle. Okay. Now, why it's called autonomous? Of course, we don't need any human intervention in the control of this robot. And what is the purpose of this robot? The purpose of the robot is that it will go underwater and whatever information you want to fetch from the ocean, you can do it. For example, you want to search for something and which goes missing from years. So you cannot just a life of a human being to go deep into the ocean and search for it. So what we expect that you design a robot and you allow the robot to go into the sea, control it autonomously because you cannot control it so wire or through some network because underwater network you don't get it. Okay, so you need to control it in such a way that you can get your desired task done. Okay, that's the only reason why we thought of okay, let's design it and let's monitor and let's control it. Okay, and I was a part of this another project, DS2 project, where like I have to travel to Russia twice, where I have to whatever algorithm we have designed for our prototype at NIT Raurkela, the same algorithms we need to deploy at Russia. Okay, and which is very challenging. Why we challenge it? Because the algorithm is the same. Okay, the algorithm that we need to implement in NIT Raurkela, the same algorithm we need to implement at in Russia. Okay, it means the sector at Russia and the Indian Outland between power with that. Okay, and we know that infrastructure Russia is very high as compared to ours. Let's face it. Okay, so it was very challenging for us, but fortunately, so I was not alone with my team. I was like guided by two my seniors and along with my one of my batchmate also. We have a group of 4 to 5 members, and the task was to build a robot first, and second is that to propose some control algorithm to solve the specific task. So I'll go the first slide. And that's it. No problem. Really. Fine. Okay. So during this talk, I'm going to cover regarding a few topics, and I'll try to complete the entire part of it and within the time that is allocated to me. So first, I want to give an intro regarding autonomous on-road vehicle. And so, like I discussed, so you can see the applications of the on-road vehicle is very fast. Okay. So, for example, the best part is the surveillance. So for surveillance purpose, we generally use for under the vehicle, at least in India. Like whenever we want to collect some data at some point, so what we do is that we put it or robot on that. Okay. So these are like the four images that you can see on the screen is like already developed prototypes. Okay. And already tested and already deployed in production. Okay. So and as you can see, autonomous under vehicle has programming robotics vehicle that can drive or glide through ocean without real-time control by human operator. That makes why we call it autonomous. Okay. Now, I want to give what is the challenge that we face and what motivated us to go with this designing part. The real challenge is that the dynamics of this vehicle, see, whenever you want to control something, you need to know the mathematical model of it. Until you know the maximum model of it, is very difficult to come to it. For example, if I want to develop a robot, and let's say I want to develop a robot and it has an arm. So if I want to move the arm, I need to know like how it works, what's the dynamics that's helping movement of this arm. Okay, the first very important part is that I need to know the dynamics of this robot. Okay, so the dynamics of robot is very complex. Why it's complex? Because like if we leave this robot, because the purpose is that this robot should work underwater. Okay? And in underwater, a lot of like uncertainties are there in terms of wave populations, in terms of ocean currents, in terms of strong winds. Okay, so a lot of parameters that might disturb or that might incorporate in dynamics of an vehicle. So that need to be considered while designing and formulate the control laws. Okay, that is why the first motivation is that how to take care of these uncertainties while designing a law. And second is that method of work that has been proposed is that you have a system, you first that system in real time, you know all the system non-linear system. We try to first convert that into linear system and use that and put a control law so that we can control it. Why? Because we have a confidence or we are very confident and comfortable with linear system. So when linear system comes to pictures, we know we can use control laws. Okay? Why control laws? Because we can analyze the system in frequency domain and it's easy for analysis purpose. We avoid non-linear control. Okay? So that's the reason why we thought, okay, why not to use non-linear controller in our work. Okay? The third is that real-time implementation. So designing something and implementing in real time are quite more than different. Okay? Like for example, even if design a simple circuit using op-amp, have some capacitor, inductor, but when you real time, when you implement it, you will find this capacitor, inductor value are not same. Okay, so the real time values and the implementation both are different. So you need to take care of this also. Okay, like within how much time a controller is going to respond to a given task. Okay, that is what is called computation time. What's the time required to complete a task? Okay, so these are the few things that really motivated us to work for this work. Okay, then this is the objective. The objective that I said to you is that the objective is to first develop a prototype. Once the prototype is designed, then we need to have some control laws. Okay, use as control law in such a way that your robot will move in a particular direction. That direction is defined by already by the user. Okay, so this is my hardware structure where we have various units of it. So I'll not go deep into it. Rather, I'll show the prototype that is being designed at NIT Rourkela. And the prototype is this one. Like you have a robot, which is a torpedo set, okay, and what is called SBC, single board computer, where everything is being controlled regarding ROS, two ROS. ROS means robotic operating systems. So through this ROS, we connect all the sensors, we get data, and we monitor and we control your system, right? So we have some setup for it, okay. And once the prototype is ready, then we need to know the dynamics of it in order to control it. Okay. Let's say, for example, I want to control my AOB on XY direction. So I'm not going to Z direction, for example. So let's say I want to control my AOB two ways. First, in horizontal direction or in vertical direction. Okay. Let me first talk about what do you mean by dynamics of a model of a robot, and what do you mean by kinematics of a robot. Anybody can say what do you mean by kinematics of a robot? Kinematics of a robot. Generally, the robot I will define by two ways. One is kinematics, one is dynamics. Anyone who can say what is kinematics? The motion of the body. Motion of the body. Right. Thank you, sir. The motion of the body, right? So, and what is dynamics? What causes that motion? The forces under turn. Right. Okay. The kinematics tells me that how your robot moves. What's the orientations? Okay. And dynamics tells me like what is the force and torque behind those motions. Right. So you need to know the kinematics and the dynamics in order to control your system. Right. The first thing that now let's say I have a robot. So first robot can go in X, it can move in Y, and it can drive in it. So I have X coordinate, I have Y coordinate, I have Z coordinate. So in building those words, in X coordinate we have velocity, which is called U, that is surge. And Y we have some velocity in Y direction, that is sway, that is V. And we have some velocity in Z direction, that is what is called U. Okay, or U velocity, right? So these are technical terms that are associated with your robot. It may be mobile robots, it may be your underwater robots, it may be any robots. So these are the few things, surge, sway, and heat, or yaw. These are the few terms that are always associated with any robot. So for example, if I want to control a robot in XY direction, so I need to first take care of that, okay, let's say my robot need to move in first in U, that is surge velocity, forward velocity. So if my robot want to move in forward velocity, so I need to have a thruster, right, which will provide that force, right? Yes. So if I want to move angular, okay, let's in Y direction. So who is going to provide it? Because I have only one thruster. And my system is under actuated system. Under actuated system is what? Like, for example, my AU can move in how many direction? Let's say three direction, X, Y, Z. But I have a thruster which can only help me one direction. So if my number of thruster are less as compared to number of direction, then that is called under actuated system. So the system that we have designed is under actuated system with the constant of our budget. Okay. So we can only purchase only one thruster. So what I've done is that we have tried to maintain a forward velocity that is U constant. And what we have done is that through a control law, we have tried to control other parameters. Let's say if I want to move in Y or Z, then I have to give desired velocity and give desired orientation for it. For example, if we are idle, if I want to go straight, or let's say if I want to go up at this point, so what first I have to go here forward velocity, then I need to find a proper orientation so that I can reach at this point. How I can get a proper orientation? By having a distance. Okay, let's say this is alternate distance or of my AUV and the desired locations. I find some relation between these two parameters, find the orientation, and move along. Okay, and who is going to help me? My control laws. Okay, and what is then control laws? If I go with the design, this is what we call rudder plane. Okay, and this rudder plane plays a very important role, flapper, which help me to go move in sideward directions. Okay, so these flappers really help me to drive into it and also help me to move in horizontal directions, right? And these planes are called this is okay. This is my stern and this is my rudder, right? Stern and this is rudder. The stern planes help me for horizontal motion and the rudder part help me to drive in. This is fine, okay? Sorry for it. So these two help me to drive into it, stern help me to drive into it, and the rudder help me to move in a horizontal direction. Right? In the plane also, you can say you can have two sterns and one rudder. Okay, and these two sterns help me to drive into vertical direction. And the rudder that I have it, okay, that help me to move in horizontal motions. So I have two motions, one horizontal motions, one vertical motions. And the horizontal motions are being controlled by your rudder. This one. So if I go the top part. Okay. So this is my rudder. Okay. which is help me to control the horizontal motions. Okay, if I want to go to right, so it will go in reverse direction. Okay, the rotor will move this direction. If I want to go to left, it will move in this direction. Okay, and this is our form as turn films. If you can see the while you go in a plane, like the turns really move this or this, so it opens up, right? So when you want to go drive into it, it opens like this, and when you want to go up, it will open like this. So we need to control this turn planes if I want to move vertical directions. So now it's clear that yes, I have a forward velocity that is provided by thruster, and I need to provide a proper value, a proper control signal to this plane so that it can move horizontally or vertically. Here. And that is what our work is. Our work is to come up with control laws that help me to drive my system either in vertical direction or in horizontal direction, right? Okay, how many of you are familiar with the control system? Control system. Because I want to know my audience, because based on that, I'll go dive into it, or like I'll just try to know like what is the context, how you design it. It's a maths, because when it comes to control system, it's a math. So I'll not go deep into the math. So what I'm trying to say is that yes, my system, my kinematic equations, that is my motions, have been defined by this set of equations, and my dynamics, that is force and torque, have been defined by this set of equations. Okay, and what is my objective is that in real time to identify the dynamics of my system. See, when you design prototypes, okay, even if you have followed, you have taken a reference of some prototypes to design it, but let's say we have taken a reference of AV called infant AV, okay, and it is very popular, and that is deployed in the Russian government. We have referred that and we have designed. Even if we design it, do you feel like we have created the same replica as that of infant AV? No, because see, we have taken a reference and designed it, but the design variable might be different. Okay, but we need to know about it. How to know about it? Okay, that's where we use something called AI, a machine learning. Okay, so what we have done is that we have tried to analyze this dynamics of my system. Okay, if you remember control system, basic control systems, I have something called x dot equals to ax plus bu, and y dot equal y equals to cx. This is clear, right? So what is x? X are my state of the system. What is y? Y is the output of the system, right? What is A? A is the state matrix. B is my control matrix, right? And C is my output matrix. Or it can be vector, right? Now what I'm trying to say is that now, for example, these are my states of the system. What is V? What is R? Okay, let's say I want to control my AV in horizontal motions. Let me focus only in horizontal motions. Now, if I want to control in the horizontal motion, now you tell me what are the parameters that I need to consider. In little words, no technical words required. Let's say my AV here. So I want to control my AV in horizontal motions. Let's say I am here. I want to go at that point. So how to go? First, I have to start a motor. That is first step. Give a power supply. Okay. So that the rotor will start in forward direction. U. So in our case, we have considered U to be constant. Okay. So if you can see in this dynamics, I have something called U. Okay. And this U is my surge velocity. It is constant. Right? So what else? Because I have to go at that point. For my forward velocity drive me X. So I want to go in some direction. So how to go? So I need to find, I have to go in this direction. So I need to find V and this angle, that is R. Okay. So I need to estimate the value of V and R. Right? How to estimate V and R? So I need to, that it means for my system to be controlled, so I need to identify this V and R first. Right? Because these are the states of my system. Is that is clear? Okay. So how to identify this? So if you analyze this equation bit clearly, okay, so you can see what is this? These are the coefficients. Okay, for example, y x dot equals to ax. What is a? A is a coefficients. Okay. Similarly, so these are the coefficients of your infant AV, the AV that we refer. Okay, right? These are the parameters. These are the parameters. Okay. Right. So in these equations, what is important for us to know? Yes, they are in form of x dot equal to ax plus bu. Right? Okay, but no, they are not non-linear, is not a linear equation. X dot equals to x plus bu is a linear equation, but I have a non-linear equation to it. Why? You can see two terms are coupled over here, right? U and R. What is U? Forward velocity. What is R? Angular. Okay. So even if this one, you can say this one are my what? What are my coupled terms? So they are non-linear equations. So my V is what? Motion along y-axis. Okay, it's nonlinear equations. So this angular velocity is also nonlinear equations. That is R. But the things that we got it from your infant AV is that your angular velocity V depends on two arguments. One, U, another R, another V itself. Okay, it means I have two states, two states. Let's say your V is one state, R is second state. Okay, so if I want to control V, how to control V? V dependent on forward velocity, U, R, and V is own state. So if I want to control this V, U is constant. So what I can control? I can control my own state, own positions, or R. Okay. Now look. Now if I want to control R, now let's see how R is dependent. R dependent on forward velocity, U, then U, again U. I'll not touch the scale. U, R, there's another term, tail of R. What is tail of R? A rudder angle. That is rudder part. You know what orientation you should go so that it can reach at that point. Okay. So if I want to control V, I want to control R. If I want to control R, I want to control U. So I have to give input to tail of R. What is tail of R? Is the control input. And what input I should give it to this rudder, okay, so that it can move, so that it can reach to this point. How it will reach? By giving R, buffer R. If I give buffer R, then buffer V is defined by default. Okay, so it means V dependent on R dependent on tail of R. Is it fine? So the objective now henceforth is to design a controller so that I can control this tail of R in such a way that I can reach a desired position. You find this part is clear? Okay. Now, so you know U of K is dependent on, sorry, V of K is dependent on U, no U because U is constant. So V and R are dependent on R and tail of R. This part is clear. So can I write V of K is a function of V of K and R of K, and R of K is a function of U is constant. So V of R of K and tail of R. This part is clear. What is F? Nonlinear function. What is F? Nonlinear function that relate my state with that of dependent variables. Yes. Okay. And this is what is being formulated for neural network. So I just wanted to know, I see for my neural network, what is neural network? We just try to relate your output to your input. We just try to find the underlying phenomena which connects my output to input. And that underlying phenomena, what is called non-linearity, right? To attribution functions. What is my role now? See, my role is, let's say, black box. I have two states. That is what? I have some inputs. What are the inputs I have? U constant. Then tail of R. Two inputs. I have two inputs. U constant. Okay. U always constant. Then the tail of R. Okay. If I this, then what will be my states? V and R. Right. So inputs I give it, and output I should get V and R. So at every instant of time, I should give, by giving input, I should get proper V and R. Give an input, get V and R. Get a given input, get V and R. So that you can drive and reach a desired position. This part is clear to you. Okay. Now, how to do it? Okay. Let's start. Before going to the slides, maximum formula. Let's talk about how we do it intuitively. Okay. Now, how you do it? First, I need to know like how my del of R and U depend on V or R, or in other words, how my V and R, that the output of the system depends on the inputs. Yes. Yes. So what we do generally, that what I've done at our research doing our lab is that we have a prototype, we have a swimming pool. Okay? So what I've done is that we give random inputs. We give random inputs and we allow the robot to go whatever you want. Let's say I give random input every instant of time and it covers all frequency of time. I'll give an input in such a way that it covers all frequencies. Okay, right? So I give, let's say U constant, del of R. The del of R is my control input. So I fix U and give del of R. Okay. So now it will move in which direction? Randomly, it will move. Okay. So what is my purpose? My purpose is to collect data now. If I have data, then only I can build a relationship. Because ML mainly depends on data. More the data, better the result, better the mapping, or better the relation between output and input. Okay. So to collect data which map your output and input, I need to have your feature matrix and your output. Okay. A dependent variable and independent variable in your ML literature. That's the word that is given. Okay. So in order to find a model or build a model, I need to know my features and my output. Okay. Feature matrix and my output column vector. If that is clear. Okay. Now in this case, what is my feature matrix? U and del of R. What is my output? V and R. Give random input, get V and R. Once I get V and R, let's say I get data, let's say 200 data, not 200, not good enough. Let's say I have 1000 points of data. Then I build a model out of it. Which I have model? Neural network model out of it, which maps my input to output. Once I know that model, then it becomes quite easy on my path to design a controller. Why? Because now the maximum is clear. Okay, the maximum is clear. This means I know that what is the equation that relates my output to input. Now, which parameter I need to control, that is known to me now. Now use a control law and drive it. Okay. So the majority part is that you need to first identify the mathematical relationship that governs that relates your output to inputs. Right? In which direction I should go so that I can get the desired force, or desired third, or desired directions. Okay. So what based on your task, you first identify your problem statement. Okay. Your problem statement is that I need to identify the dynamics of a robot. Okay. For that, I have to give random inputs, get the random outputs, have it, then build a relationship. Okay. This part is clear. Once you know the relationship, then you build a control. Okay. So we have a dynamics. And what we have done is that, so you give an input, U of A. We have also have del of R also. That's this actually. The two input del of R and U of R. Give it to the system. Okay. So when you do it in real time, identification, how to do it? You know real time identifications. See, a system can be identified in two ways. One is offline, one is online. Okay. What is the use of online identification? What you call adaptive? Anyone? Come on, tell me. Okay, let me take the example of Tesla. Okay. So you have something called, okay, there's something called computer vision associated with Tesla. What is that? Tesla is a driverless or a driver car. Initially it was driver, now driverless. How it works? Automatic. How it takes decision? This camera connected to it. Then it captures connected. then take a decision online. At that very instant, it takes a decision. Then suddenly, like the car is going, suddenly, like say, a dog crosses. Dog never crosses there. Let's say it crosses. Then suddenly they have a break. So who is going to monitor over here? So that is what is called online identification. So when you do something online, at that very instant, it becomes very tedious, very tough. Suddenly, let's say for example, your ship is going, and suddenly your weather condition changes. It's strong wind, strong ocean current, and strong waves. And if you have not designed a system in such a way that it can counteract this speed, then the system is going to collapse. The seed is going to collapse, right? So you have to take care of this. Okay. So your system is going on, suddenly there's a wave, huge wave. Still, it always be stable. Okay, it will not go into oscillating mode, or even it goes, still it will be stable. It will oscillate, then again it will be stable. Okay, that is what we call online stabilization. Okay, so your model should be identified online and offline. So what's the benefit of online? Let's say offline. Offline क्या है? आपका कार टेस्ला कार आइडेंटिफाई हो गया ऑफलाइन. ओके, मतलब क्या है? फॉर स्टैटिक ऑब्जेक्ट्स. मान लो इस रास्ते में मुझे जाना है. Like if I want to go in this path, I know what the timing of the traffic. I know what are the trees. Okay, I know what are the things that I need to avoid. Okay, I have trained my model based on that. Okay, I have trained everything. Okay, the static object, dynamic object, everything I have trained. Okay, now I'm in position now. That's offline training. Now I'm in position that I can allow my Tesla car for testing purpose. Okay, but suddenly, okay, and suddenly I saw that a Tesla car suddenly stop at that one point. Why? Because, or let's say it moves. Okay, even if a cat crosses or a dog crosses, okay, it ramps over it, crosses over it. Okay, it means what? Your model is not properly trained on that. Okay, right? So you have trained a model which are available to you all. You never imagine that, okay, a cat in USA is going to cross your way, right? Or a dog is out of the box, right? But when you do in real time, every possibility will take care of it. Okay. If you remember this popular event during Google Lens, you know Google Lens, right? Yes, everyone. Have you heard of this scam that's called something called not Anaconda or Gorilla? Have you heard this Gorilla associated with Google Lens? Any one of it? Don't type right now. Right? ChatGPT gives a lot of information. With some time abstract also. Have you heard of this word? Okay. Now let's say in nowadays, what happens is that if you see something and if you want to know the brand of it, what you do is Google Lens. And it will give similar images. Okay. So generally what happens to a couple, okay, and they generally post their photos in Facebook. Okay. And one, they post a photo of the car, brand is known to. But when we click a photo of his girlfriend and post it in Facebook, and someone in Google Lens scanned the photo of their girlfriend, and it turns out it's a gorilla. Okay. Right? Unfortunately, you won't believe that was a huge challenge for the Google. It means the data they have used for train are not sufficient. You won't believe within 1 day that person become millionaire because he filed a case against the Google and he can heavy amount for it. Okay, it means what I'm trying to say is that you need to have more and more data. Until you have your more and more data, you cannot build a model. Similarly, if you want to design a robot, first the dynamics should be known to me. And to know the dynamics, I have to give the input in such a way that I give input in all frequencies. ऐसा नहीं हो सकता है, ओके, एक इनपुट एक फ्रीक्वेंसी में वो आउटपुट आप दो टर्न कर ले, काम कर लेगा नहीं. I want to vary my input in all frequencies, determine the outputs, okay, then you map your models. ऐसा ना हो कि लाइक एक पॉइंट के लिए आपका मॉडल linearly मूव करे और एक टाइम पे नॉन लिनियर मूव करे. So your data should be sufficiently rich, okay, then only you can build a model, right? That is the fundamental of your ML, which we already know about. Okay. So now, what is ELM? Why we went to ELM? Is that, see what I said in first slide, computational issue. Okay. So when we think of, okay, in this paper, let me talk about, because this is AI ML workshop, let me talk about this way. In nowadays, everywhere we are using deep learning, right? Everywhere. So I'll talk about few papers where like unnecessary they have used deep learning and they have published paper in standards, right? But there's another paper, I don't remember the name of that paper. So the paper title is something like tree structure models versus deep learning, something like that. Okay. And it's clearly stated in that paper, and that paper is like a hot cake in the market. Within like few days, the paper is cited like in thousands. Okay. And that paper claims that, see, if your data is labeled and structured, and you have a data labeled and structured, not necessarily always deep learning is going to give a better result. Okay, you can have a tree-structured models which can give a better result and can challenge a deep learning model. Okay, they are not claiming that yes, deep learning cannot perform. Yes, they can perform, but see, when you have a deep learning model and when you have a random forest, if you know random forest, decision tree, then which model you will prefer? Come on, tell me. Let's say I have both. I have a machine learning model and deep learning model. Let's say I have a random forest. I have a, let's say, CNN models. Both are used for classification purpose of audio signal. Which one you will prefer? Deep learning. Okay. I will prefer random forest. Okay. Why? Come on, tell me. Both give accuracy same. Both the model give same accuracy. Competition. Okay. See, when you save a CNN model, how you save? .h5 model, H5 model, right? And when you save a model, you deploy it. Similarly, we save a model and deploy it. When you save the model, just see the size of the model. Okay, maybe it will be CNN will be in some MBs, it will be in some tables. For the time complexity of this system is very less as compared to CNN. Okay, so if you want to analyze time complexity, just go through a data set, the algorithm part, and you will know like if you compare the time complexity of your decision tree model as compared to CNN model, the decision tree model is quite less as compared to CNN model. Okay, so you can challenge, like if you have a paper published, which recently we have done, I don't know how the comment will be, like they have published 2 or 3 transactions based on, like they have a data set already, they have shared the data set. Okay, now they have said, they have told that, okay, they have used this CNN model for classifications. Okay, and they have few papers on that. The classification, then they are gone with generative AI, a lot of things they have used. So our role is that, okay, to avoid this deep learning wherever required. Unnecessarily, why to burden our systems? The things that can be easily solved, why to use a deep learning for it, right? Okay. Now coming to our contest, our first purpose is to computational burden, right? So to make computational burden, and this is work that will be done in 2018 around. Okay. So at that time, we thought what to do, right? Because when you have a neural network, real time, straight up, because you know neural network backpropagation, right? Yes. So when you talk of neural network, backpropagation. What is backpropagation? You have a model. Okay, you have data points. How you train your model? You have data points. You divide. Simple words. If you know about it, it's very simple. Your data points, you divide in 2 parts. One is training, one is testing. In training part, what you do, you train your model. And when you train your model, you determine the parameter of the model. When the parameter of the model are being done, then you give your test inputs. You determine the output. Then you match the output with the test output. If they are equal, your model is accurate. If not accurate. Right? Yes. But how the system works? You get an error. Okay. Then you back propagate this error from output to input. You first change your output weight matrix, then go to hidden matrix, then you can go with the biases that is connected to hidden layer. Is it clear? Yes. Next, talk about like you have 5 to 6 hidden layers. Okay. Then every time it takes a lot of computation effort. First, output weight could change here. Then second hidden layer. Then third hidden layer. Then second, first hidden layer. Then you come to the biases. You change every parameter of your model so that your error can be minimized. Do you agree with this? But the benefit of VLM model is that it's a single forward network. It means I have only one layer, like RBS. Okay, what is RBS? RBF generally have multiple layers. Okay, let's talk about ELM. We have a single forward network. It means I have input, I have a hidden layer, I have an output. Here, okay. And ELM tells me is that it's already proposed by NTU. Okay, 9th Technology of University in 2000, back 2016 or 17. Okay, that time it was proposed, which proposed that see in ELM you don't use back propagation also. Okay, what it uses is that we already fixed your input matrices and hidden layer matrices with a value between -1 to 1, right? Because they are derived a mathematical relationship and they have proved that if I take the weight of input and hidden layer and fix it between -1 to 1, always my output result is going to converge. Okay, when the output means error is going to converge to 0. Okay, so no need to change this, update the value of input arguments or your output arguments, right? Right, it's clear to you. So let's say you have 2 neurons input, you have 4 neurons hidden layer and 2 output. So all are like connected to each other. Okay. So this side you're not touching anything now. Initial आपका neural network में क्या होता था? Like you have the error, you tune this output, then you go come back and you tune this input. Now ELM states me that no need to touch this one. It's already fixed. You take a value of -1 to 1, any value, then it is always going to converge. That is guaranteed. Okay. And then your objective is to only determine your output. Output what? Output matrix, weight matrix. And which is very, very easy. Okay. It means your computer burden nearly divides. Let's say you have like 6 hidden layers, for example. You have 6 hidden layers, then you are only changing the output matrix only, right? You are not focused or bothered about the input or your hidden layers. Okay. You only bother about the output layers. So SQL animation tells me that you only determine the output weight matrix. Once determined, then you give the input and get the result out. Okay. That's why we are proposed to use TLM in our approach. These are some mathematical equation. Okay. Like general equation. So this is my activation function. And this is what we have input, output, combined with the input, and then we have a bias to it, and we pass the input to your activation function. Okay, and this is the general fundamental of your neural network, right? And this is how you would minimize and you determine what are the optimal value of this output matrices, that is W, right? One that is fixed offline. Now you go for the controller design. Okay. If we talk about the structure, that should be good enough. That is going to mathematics. So what we have is that okay. Now let's say, for example, this black line tells me like, see, this is my reference. I want to track this. Okay. It means what? Let's say I'm standing over here. Okay. So I want to go 90 degrees. Right? Again, move here. Again 90 degrees. That's left. Okay. Again 90 degrees. It's just like a pulse. Okay. So let's say this is a reference. And we're going to do on the surface of the water. And we're not going inside the water for the time because we are focused only the horizontal motion of the flow. We start a robot and we give a reference. See, you need to track 90 degree to a right, 90 degree, then left 90, then right 90. Okay? So just like a pulse. Right? You give this reference, and what to expect is that you give a control law in such a way that it tracks a reference. Okay. Now, what I'll show is that before going into the simulation, I just tried to show the video, that's heading part. Okay. With the audio. Okay. Heading. No, heading part. Just mute the video. Pause. Pause. Yeah. So this is swimming pool at energy all. And what are the objectives that if I leave my AUV over here, it will go in this direction, 90 degree, again 90 degree, then 90 degree, then 90 degree. Okay. So this is a reference that has been given, and we are doing it autonomously. Like we are designing control law. Let's first see the video, how the control law has been proposed, and how we are achieved. Then I'll go into it, how you are doing that. Now, just AV, just tracking it. Okay. We're not forcing AV. We're just through the control law, we're tracking that you move. See, exactly you're not moving 90 degrees. It takes some orientation, of course. Okay. This is my rudder. It's moving properly. The rudder mover helps me to move left or right. Okay. This is my senior, rudder out. He's now upward. Okay, so for tracking, I've been done. Okay. So, the diving part. The diving is that. Pause. Diving is that you allow the AV that you maintain a proper height. Okay. And the difficult that we face in swimming pool is that you don't have proper height at level everywhere. That's initial part, the height is low, then you go and dip. Okay. So we have make it common. Let's say I want that you're on the steep floor, okay, or the height should be like let's say 3 meters, for example. So I have to first set it and I give it to my AV so that it will go inside the water, maintain it, and then you come up. Okay. Now it goes, stays continuously at that level. And we have connected some wires so that it don't get hurt the walls. If at all a control fails, and then suddenly it will get up. And this is our MTech student. Oh, sorry. Go back to the slide. Yeah. So the purpose is that we gave a reference signal, and the role is that to give a purpose signal to my what? Rudder. Okay. Now what I'll go back and try to cover up this one controller. So what is my objective? My objective is to get this RT. See, the reference is fixed. Reference means which direction I need to move, that is fixed. The only thing is that I need to determine, okay, in which way to go. Okay, who is going to help me? The kinematics guidance. The kinematics is going to tell me, like, see, it is giving information to the robot that in which direction you need to move. Now your dynamics will tell me, see, to move in this direction, you need to use this force and this turn. Right? So I need to have two controllers. One is kinematic controller, one is dynamic controller. The kinematic controller will give me a proper direction in which direction you need to move. And the kinematic will tell me what need to be your force, what need to be a turn, so that you reach to that location. Is it fine? So this kinematic guidance law, you give a desired path. It does some sort of calculations. What sort of calculations? In simple words, this is what it does. Okay? Let's say it just tries to follow we have used three approach. One of the approach is thread finite approach. What is thread finite approach? Anyone know about it? We call it SF. Any idea? Let's say I have a system and I want to track a reference. Okay. So what I do is that I first create a local coordinate system. Okay. What is local coordinate system? So let us assume that I have a frame that always rotate around the path. Goes back, comes back, goes back. Let's say just putting a pointer on it. It goes continuously and covers the path, reach the end, then comes to the front. Continuously move. What my objective is that the robots should track this local coordinate system. Okay, right? Yes. See, I have a reference path defined, already given by the user. Now I define a local coordinate system onto it. When I say local coordinate system onto it, it means I assume or I define like, okay, see, I have some model placed on the reference path which continues goes on moving. Now, what is my objective is that to track that moving path. Okay, and that one that goes on moving, that is what is called threaded finite. Okay, so this is my robot, right? This point is my point on the threaded finite because this is my path that need to be covered. So what I do is that at every instant of time, I find the error and I try to minimize this error. And when I try to minimize this error, what I'm going to get it? How to minimize this error? Come on, tell me. How to minimize this error? If this point which is over here, if this point which is over there here, it means my robot have reached the desired locations. It means I minimize the distance. Not only that, I also minimize the orientation. In which way I should go, so that on which angle I should go, so that I can reach the reference point. Yes. So the kinematics tells me in which direction I should go, so that I can reach over here. Okay. So for the threaded finite, that information I get it. Okay. So that I get it R of D. Okay. Now R of D is what? The direction. And this direction is acting as a reference to my dynamics controller. Okay. It takes a reference. Then what it tells me is that you take this reference, you formulate a control law so that it takes a proper direction. Goes in a proper, takes a proper like it gets required force and turn, and it will go in a proper direction. Right. So you can see over here, I have a robust MPC formulation. What is MPC? Any idea? What is MPC? Model predictive controller? Any idea? No. See, model predictive controller is very popular actually, very popular controller, and you should be knowing. You should be knowing about, like we should be knowing about it. Okay. So model predictive controller is very popular. In fact, it's like the word itself, model predictive. What does that mean? The model will predict. Okay. It means, like for example, ma'am, if she started from here, and she goes over there, right? The moment I see her at that point, my model should predict, okay, she's going to rotate and come there. Okay, it means I'll predict in future. Okay, I'll predict in future, assuming the constants. What are the constants? Okay, there's a chair on the way. Someone is coming on the way. Okay, so these are the constants that need to be avoided to fulfill our requirement. This part is clear. So this is what is called model predictive control. So you predict 5 steps ahead or 10 steps ahead based on your algorithm. Okay, you generally predict 1 or 2 steps ahead, because if you predict, let's say, for example, I'm driving a car, then I predict, okay, after 5 seconds, I need to take a turn. I'll fix it. But suddenly, a dog crosses. I'll hit it, right? So of course, what I'll do is that I predict 1 second, then I take a correction. 1 second correction. So I can predict for a long duration, but if you do it, then the control may fail. Okay, may fail means in online. Okay, right? Clear? Okay. So model predictive control is that only. Like you predict what will happen in future, looking into the past and present scenario and future constants. Right? So what is the constant? See, when we design your system, you might have some constant. See, I have a rudder which can move this and it can move that. Yes. So my rudder cannot move complete 90 degree and complete this. Like it can move within this range, right? 48 degree and 48 degree. Plus 45 minus 45. Okay. So I have a constant that I need to design my controller in such a way that it can reach the desired position even if with this angle also. Okay. So I don't need to move entire this rudder. Half of the rudder move, I'll get the task done. Okay. So I need to use all this constant to formulate my like controller and go with it. Okay. Now,
From what part first you try to do it to ELM model, then
first ELM model comes into this one. Once you need to know the dynamics of the model. Okay. To know the dynamics of the model, it means the maximum relationship that connect output to input. That is been known by ELM model.
then
ELM model is just doing the job of system identification.
how that where moving the path, how you are trying to find out that, because what would be the best way of moving that? How it has been.
Okay. Okay. Then I have to go to mathematics of it. Okay. So what I try to say is that's what I'm trying to say. Let's say this is my path that I want to move. Okay. Or let's say I want to go into this part. That is good enough. Installment part to explain also. Okay, for example, my system is over here. Now, this is the work that has been published in Elsevier, and the purpose was is that surveillance purposes. Okay, surveillance purpose. Let's say, so when I attend any party, for example, there's a biscuit over here, there's a tea over here. So I first take a tea, then I can have a biscuit, then I can have a chair. So I collect points from this point one data, and take my position, right? Similar, that is what called surveillance. Surveillance is that you go around the point, get the data done, and give it to your the one who is controlling it. Okay. For example, let's say I want to cover these 3 points. Okay, and I started this point. So what I do is that I have to first draw a hyperplane. Hyperplane means what? A distance between this to this. What is distance? You have different types of algorithms. What I'm trying to do is just try to find the equivalent distance between these 2 points and go in. Okay, and minimize the angle so that I can follow the different path. Okay, now once I reach this point, of course, I'll get information of this point and from this point. Okay, now your controller is going to tells that which point is near to you by finding the distance. Not only distance, the orientation also. Right? Apart from that, you also have something called acceptance rate. What is acceptance distance? Acceptance distance means what? Your AV should sense like your Wi-Fi. Your Wi-Fi have a reason, right? After some reason, it will not get connected, right? Similarly, your system have a acceptance area, right? If it comes under this reason, then I can go to that point. Else, I cannot cover. Okay. Similarly, we have defined an acceptance region, let's say 5 meters. So any point, let's say I have a point over here, 5 meters, and this point is 6 meters. It means this point is close to it. So I'll go to this point first, then this point. Okay. So this is what we have done in our work. Okay, for example, what I do is that this red points are my coordinate which I need to track. Okay, let's say I start from this 0, x0, y0. So I give some points. Okay, let's say surveillance of a agricultural field. So go to this point, monitor the agriculture. Okay, so what I do is that just like drones. Okay, it will move underwater and will move above water. Right. So I give this coordinate system to my systems, and the water system will go. It just follow a straight line equations. It just try to minimize the distance and the directions. Okay. So you can, if you zoom out, you can see. Not zoom out. Minimize. Okay. You can see from this, it takes straight. Suddenly, when you find 60.2, it tries to move. So now tell me, when it tries to move, I should get a control input. Yes. So you can see control input. So at this point, you can see coded samples. So I get some input informations, like some signals that you need to rotate in these directions, so that I can rotate. You can zoom it, you can see it's not a straight line, it's just a move. Okay, right? Which doesn't coincide with 60.2, but near to it. Okay. Now again, after rotate, it follows a straight line. Then it takes the motion around it. Okay. Then we just use a hyperplane equations, try to minimize some objective function, and that objective function is a convex optimization problem, where we try to minimize the error in terms of distance and the orientation. Right? Okay. So by giving you certain inputs, you can see whatever points we have. Certain input. And this is what we get to another experiment. So the basic objective of your algorithm is that another simulation spine, where I need to have different points placed, and what is my objective to track it. Okay, and we have different controller purpose for it. First controller that we are using different type of model prediction, right? And we have used different type of ELN models, right? First, we have used offline models, then we have used a linear model, then we went with online model of ELN, then we tried to add some disturbance to it, okay? Because that area also covers noise also, right? Let's say my AOV system is going, suddenly I get a wave, suddenly I get a ocean currents, suddenly I get a storm winds. So my system should be robust in that, okay? How much disturbance I should give it so that I can solve it, right? And that is what we have done the work. In this, let me go to the simulation. Okay. So for example, what I've done in this, I just go to objective function. What my objective function is that I have a linear system, I have a non-linear system, I have made it linear at every instant of time using Taylor series. Okay, once I get a linear system, now then I have to define a control input. What's the control input? That like what are the things that you need to control? For example, I need to control x of I at the state and your inputs. Okay, right? So now I need to define a norm. That norm is called H infinity norm. What is the H infinity norm? It tells me like, see, you have a set of WI. What is set of WI? The WI stands for a set which consists of different disturbance. Okay. Now you need to find what is SUP means. Super, right? Or maximum value. Okay. So out of this WI, which value is maximum? Okay. Which the transfer function can tolerate. Okay. It means maximize this objective function such that it is less than this gamma function. Okay. And you get a proper value of WI. What is WI? WI is a combination different value of D. What is D? Disturbance. Let's say W stands for D1, D2, D3, D4, D of 10. Okay. Now I need to find out of the different disturbance that you give it to the system for testing purpose. Okay. You observe, because when you use your prototype in real time, before you deploy that, you should test it. Yes, right? So when you test it, you should test all the possibilities, right? Similarly, before I deploy your system on our swimming pool, I need to find what is the maximum disturbance my control algorithm can take. Okay, and for that I need to find it through a that is called H infinity norm, which tells me, which gives the bounded conditions like, see, For this, if you minimize this one, you will get the value of disturbance, and this disturbance can be allowed for your system only. If you go beyond it, system becomes unstable. Okay, right? So this information is given by solving this H infinity norm. And I'll not go with this minimization. So what I'll do is that I'll go with the simulation part to tell you like what I've done. For example, this is my reference. We try to solve, we try to like move our controller so that it matches references. And this is my proposed controller. See, what we have done is that we have tried to merge H infinity controller with model battery controller. And the proposed algorithm is just a hybridization of H infinity controller and model battery controller. H infinity controller takes care of robustness, and model battery controller will take care of the future that is going to happen. Okay. Now, after this, we try to compare with H infinity control that was proposed 1 year back for this. And we found like this is my blue color, that's the control that we developed. And we found it tracks easily with less time. Okay. And it covers it. Okay. So while tracking, we observe the maximum disturbance that the system can tolerate is this one. Okay. Sorry, is this one. Okay. It means maximum it can tolerate 0.01. And we have minus 0.1. It means your disturbance can oscillate between minus 0.01 and 0. Plus or minus 0.01. Okay. If I give a disturbance in magnitude, beyond that, the system becomes unstable. Okay. So what is the purpose of this H infinity control is that to design a control taking some constants. First constant is that your input should not be like should not cross this like the rudder. The rudder. Because when I say constant means what? Let's say, for example, let's say in nowadays, in every house, when you have a motor, use a motor, water flows, like top flows. By default, automatically it cut off, right? Why? Because you have a sensor, right? Okay, and that is a constant. Its constant is that it can go up to water level, let's say 10. Okay. Similarly, I have a constant is that my rudder can move maximum to plus 45 and minus 40. Okay. And that constant we converted that degree in terms of radian, and it comes out to be 0.7856 and minus 0.7856. It means the rudder angle should vary between those constants. Okay. Right. So you need to formulate a control law in such a way that you need to take care of the constants, solve it, and reach your desired plan. That is the objective. Okay, doesn't mean like you will get everything, right? Like for example, when you design some robotics, you have to make some compromise. And the compromise that we have made is that yes, I have a rudder, you cannot move minus 180, minus 90, and minus 90. Okay, so I have that it can go maximum to minus 45. That's a constant in physical parameters, and it can go here plus 45. So the constant, I took it while solving a problem, and I observed like while tracking the reference point, I observed my control signal, my proposed blue color lies within the constant. Okay, because I have taken the constant while formulating the control law. Right? That is what is control law. That's all this derivation are all about. It's all the minimization that I have done to have the constant satisfied. Like we have different conditions. So we have the objective function. Okay. Maximize W. What is maximum W? What a maximum disturbance your system can incorporate. Okay. And minimize U. What is U? Control input. What's the minimum control input I should give? Minimum control input, what does that mean in terms of energy? Okay. What's the minimum amount input I should give so that the maximum disturbance I can tolerate and give it to my system? Okay. So it's just like a min max optimization problem. Okay. First, I need to maximize the problem, then I have to find the minimum of control effort. Right? Okay. So this is a min max of this subject to condition given by 20, 21, 22, 24. What are the conditions? That is constant. Okay. This is, for example, constant of inputs. Input can be given to this to this. Your output can be between this to this. So you can have lot of constant defined for your systems. Take these constants, solve the optimization problem, and come up with the solutions. That's what tells us about your optimizations. Optimization means what? You go from this part to this part, how to do it. Okay. Condition is that you cannot divert. So when you design a Tesla car, your part is that I cannot go on the footpath. Okay. That's the constant. I should be like, I should leave some margin. Okay. To my left, let's say 1 feet, and to my left, right, 1 feet. So I give this constant and I should move on. Okay. So these are the constant while you give it for your robot also, right? Like, for example, if you have seen this movie CTTC, right? Initially, we don't give any constants. So because of which the decision was rapid. Once you give some constant, train it properly, then the decision is very good. Okay. So, but that need to be taken care of it also, right? So else it will be tough. Okay. So random value means you are determining the control input every instant of time. Okay. So for example, I'll come to you. So for example, see, when you move in a straight line, when you move in a straight line, there's no input means input to what? Input to, come on, input to rudder. Rudder is the one which tells the directions. So when you go in 0 degree, so there's no direction. So no control inputs. So 0. Right? So when I want to move 90 degree, so I have to give a signal. Control input. So the control input changes. You can see control input changes. Okay. Similarly, again it remains constant. Okay. Because it goes on motion from here to here. See, at this point it takes a motion. At this point it takes a turn. So when it takes a turn, it gets an impulse signal. So it gets an impulse signal. But it doesn't converge immediately. It takes some time to convert. It takes some time to convert. Similarly, it takes some time to come to 0. You can see here, then it takes some time to convert to 0. Okay. Then again, it takes another 90 degrees. Again, it gets a pulse. Then again, it takes time to settle. So the control input varies at every instant of time. Yeah. You have a question? Not second in terms of, it depends on your unit. It's just one step ahead. No, because you're predicting the future. It just, you get an input, for example, let's say, for the project I'm currently working on, one DST project. The project is that, let's say you are going in a car. Let's say you're using a microphone. Let's say you're using a earphone. And now your phone, you have an ANC. Okay. Because in that project, I am the PI. So you have ANC. And what is your objective is that, what is the role of ANC? Your ANC, no, active noise cancellation. So when you buy a earphone in Flipkart or Amazon, you can say your ANC system is there, right? And because of that, your the cost of like 300 goes to like 700 or like 1700 or 1800 or 2000. Okay, what is the ANC tells us? The ANC tells us that when I'm talking to someone, if I get disturbance, let's say I'm talking to you, and if I get disturbance from the outside, it can remove it. How? I get a disturbance, let's say sinusoidal, so I generate a disturbance in opposite direction. Sinusoidal, so I generate opposite sinusoidal, so I cancel each other. So the earphone, so let's say I have a headphone, then the headphone I have a sensor, okay, and that sensor picks the signal and immediately it releases the signal. Okay, gets the signal, then it forwards the signal. Now you talk about model predictive control. Okay, now let's say I'm going in a car. Okay, your objective is what? I should have an ANC. I should not get any disturbance. Right? Don't you feel that is good or bad? Bad, why? Yeah. Okay, कुछ emergency आ गया, fire alarm, there's ambulance we need to take care of. Very good. That's the reason. Okay. So because I want to like all the noises should be removed, right? Now the car, there's no actually no noise. अभी जो गाड़ी इलेक्ट्रिक गाड़ी आता है कब आगे पीछे खड़ा हो जाता है we don't know, right? Absolutely no noise, right? Electric vehicle that we have, okay? Now we want noise should be there with the car, electric vehicles, okay? So that I can know that the vehicle is coming behind me. Okay? Now when you are going in a car, okay, your objective is that when I get an ambulance noise, I could hear it. So I could have a device so that is sensitive to some noise frequencies. I should not remove all frequencies. I should remove frequency of my interest and allow a frequency of my interest. Let's say I want to hear the noise of, let's say for example, ambulance, fire alarm, site, and in the government website you go, you can find they have frequency bands, narrow bands. Okay, so you define narrow bands and allow them. Okay, you forget this noise, bypass. Other neglect. Okay, for example, now when I'm talking something to you, okay, I have a system controller, model predictive controller, and you can feel okay, someone is going to come. Okay, bit of information also it controls, right? It takes action in future. Is there a point? That's important model predictive control. Model predictive control means what? Before it corrects, before the things goes wrong, it takes action. Right? Based on my present and future. Let's say I get disturbed because my thing, no one is going to match a human being. Nothing. Okay. Right. Even AI now, even after 20 years or 30 years, because I'm very like young to say, okay, like even I'm in 40s, right? Even after 20 years also, nothing is going to replace because our mind is very complex. The way we take decision, no one is going to take, right? So let's say a sudden decision also we are going to like now based on our information present, the model predictive control is going to take action. That's going to happen equally. Okay, that's why model predictive control is very popular. Okay, like because of that we have explicit model predictive controller, we have variant model, different variant of model predictive controller have been developed in literature. I have just used a simple model predictive control. It takes action in futures. Take a present scenario and put action in the futures. Right? And if you take a long step prediction, then of course the chances vary is that you might come with an error. In model prediction, see, my aim is that when I enter, okay, I never expected question from you, right? Right? See, I go on talking like that is model predictive control. Like I go and talk for 1 hour. But if I put a constant, like someone might ask the questions related to these topics and optimize it and come with the solutions. So before you ask, okay, I'll prepare myself. Okay. So don't you feel like, yeah, if I'm prepared, it means your model is good. If you're not prepared, panic, what you will feel? क्या पढ़ा रहा है कुछ ही बोल रहा है कुछ समझ नहीं आ रहा है. See, your model should be prepared to respond. If that is done, then your system works. Right? That is all of model predictive control. Okay, the moment you say something, it is going to give you information. Right? That's like in future. Okay. Like if you take a long time to predict, like कल क्या होगा? It's a long journey. कल के अंदर कुछ भी हो सकता है, right? But let's say I know within 5 minutes, okay, we'll be in this room. Maybe after 10 minutes, we may not meet. Maybe I'll be in my college, you'll be here, right? So we cannot predict after 10 minutes. Yeah. So model predictor gives a better result when your prediction is late, right? Like 2 steps or 3 steps or 4 steps ahead, right? So the basic objective of this work is that we have used your AI, like machine learning technique, to capture to get data, build a model out of it. Once the model is ready, then you use different type of controllers. There are few of it. There are many controllers. When I talk adaptive controller and we talk about opposed control, there are many. And there are only just few of it. The one that we have done work. And because of this control, we can control it. Okay. And hopefully with this time constant, so hopefully like How far I am able to convince you all, I don't know, but yeah, I just try to tell you like this is about how the works goes on, and if you have any doubt regarding this field, if I can contribute to it, reach out to me. I'm at Silicon University. Okay. So currently also I have some projects going on, one or two projects. So that's all from my side. So any questions you have? No question? The publications paper are important. So, but what we believe is that that's the hype going on. Like you need to have a lot of papers. So believe me, if you have one genuine paper that's good, you need to be satisfied. So that the system, your management is going to push you. You need to have a lot of papers, lot of projects. You work on one project, not necessarily you have to have papers. Here, the system should work. If you design report, report should work. See, you have a fund. Let's say you have a fund. You got a fund to develop your robot. Right? No one is going to take the effort that you put for designing. So when you try to design for a robot at Raulkela, we don't get the materials. Because for the materials, for the small piece also, you have to wait for get data or materials from Mumbai. Mumbai, Bhubaneswar, Bhubaneswar. So also you have to wait for months to get the materials done. But if we would be in Mumbai, Delhi, ज़्यादा हो जाएगा. But रोबोटिक्स ऑटोनोमस अंडर द व्हीकल कितना इंस्टीट्यूट में बनाए गए हैं. एक दुर्गापुर में है, एनआईटी में है, और एक साइड आईआईटी गुवाहाटी नहीं और एनआईओ गोवा में. We have 4 to 5 organizations. We are developing like जो अभी तो काफी आ गया है 2018-19 में इतना लोग ही बनाए थे. एंड राउरकेला में के पास में भी कोई ओशन भी नहीं है टेस्ट करने की. And we test in swimming pool. And reality is that when you test in swimming pool, you don't have any disturbance. Okay, that's will get challenged from the reviewers. Like, go here, so kya karenge? So the system that we have, we can do it. Okay, and Bhubaneswar, we have Chilika, you can go and test it. Okay, like, or you have Puri near to you can go and test it. Okay, have a permission, go and take. But in Raulkela, we don't have permission, so we have to test it within the chapter. The thing is that when you design a robot, the entire hardware setup takes few years, few months. Okay, and all okay, output क्या है आपका? Output क्या paper नहीं है? You forget about it. Everyone will learn after the papers. Okay, and if we start learning after the papers, then okay, it's good thing to have published paper, of course. Okay, I don't have many more. So only I have I'm doing some consultancy and I'm have some papers, some work done. Okay, some projects going on. So that's what I believe. So that's a message that I would give it to others also. Like you focus on your work. I'm very young to say because many seniors are there. So that's just trying to say is that you design some prototypes, try to work on it. वो काम हो जाएगा पेपर हो जाएगा. If you have a conference also that's good, but आपका काम genuine होना चाहिए. आज बोलते हैं ना anything you put in conference तो हो जाता है. But आपको तो पता है ना क्या है आपका, right? Right? You're the one who knows about it, right? Right. So one thing. My background is not that because of one point of height, weight, bigger a lot. Comes to me, there model, final model what you have that control through the control unit or AI development. What I understood is probably to get a fine-tuned control. ML model, AI model will imply that the most control is right. So I just wanted to know whether the final model that even through the fine design control unit or a real-time AI-based to answer this question, I guess that is a combination of both. Because the yearly model that we have used is a single program network. We have only one layer. So let's say we have a CNN model. Okay, so we're not talking about lightweight model. It means we have a CNN model. Okay, and let's say CNN model we have a deep neural network model. And if you want to use deep neural network model for embedded system, you cannot use as such. For example, nowadays we are having nano build BLE 33. Okay, nano BLE 33 is a chip which have only cache memory of 32 KB, 32 MB, and you embed this ML onto it, it's not going to work. So now the lightweighted that comes is that in that chip we have facility of that's what tensor light. Okay, tensor light takes care of this lightweighted neural network. What is lightweighted neural network? It's all about tiny ML. You have a bigger structure, bigger neural network, deep neural network. Now you bring it to a tiny structure. And once you bring a tiny structure and put it on the embedded system, and it will fall. So I have started working on that. I don't have much idea regarding this tiny ML part or lightweighted neural network part. What I can say with my context, yes, you have worked on Python environment using in Ubuntu environment using scripting language as Python and ROS. And ROS help us like you have a model because our model is ELF, single photon network, very simple photon. Okay, you have it takes a lot very in KB of memory. Put it and your application solved. But here, using a CNN model for such type of is very challenging. You cannot do it actually. You get a lot of communication delay. मान लो मुझे वहां पे जाना है अभी सिग्नल मिलेगा so it will take a lot of time to do it in real time. So when you started this work, there's a challenge that do neural networks going to solve a real time problem? The answers, of course, may or may not be. You will find many papers theoretically who have challenged yes can solve it, but when you implement real time, answer is no. Right? So that's why we went to the ELM because ELM क्या होता है ना, we only determine the output weight matrices and try to minimize and get the output. जल्दी हो जाता है. But just like recursive least square algorithm. He makes that function was there where you were trying to minimize the optimal thing. Where that is being taken care, to model the control unit or model the control unit. Model the control unit. So we can like this. Since we all are faculty members, right? I guess if you have any simulated softwares, you little bit into it, you can come up how the things are going on. Okay, okay, just 5 or 10 minutes, so that can have a plan. This practice show you the complex approach of that God actually. What's it? Sorry. Was an excellent putting the things to find perfect. So that's but in addition to that, we have any which is being utilized. So that's what I said. Yeah, the simulator, we don't have any software for it. We have like we have studied using MATLAB, simple MATLAB render, we solve it, and the objective function will get it, value will get it, convert input value, give it to the system, put it in the embedded system, in the hardware, and that will take care of. We don't have any like any apps or any software that takes care of it. We have simple like MATLAB, Python, and your ROS. Okay, that takes care of it. You don't need to like give an additional you have designing software or you need to load any software for take this input. No. Only you have to take care that the hardware that you have designed that it should be good enough. Like it takes input and goes current that goes the fine path that is being taken care by yes, fine. Between also no. We actually we are not maybe some might have In our work, we just try to use machinery to capture dynamics. That's it. Okay? We are use the neural network model for controlling purpose. So using neural network model to capture dynamics. Once the dynamics known to me, then you use controller, different controller to control. But yes, controller can also be used using dynamics. So on my side, so hopefully I'm able to convey. This is what. So I just try to summarize the controller, because if I go into detail of each controller, then because first the first question I asked that control system, like I know the audience, then based on that I give the controller. I just wanted to know like how the system works, right? And what are challenges we face in working of like design of robotics. So when it comes to robotics, still we have quite behind. Okay, it's not that we are skeptical. We fear robotics. It's a reality. Okay, because like a lot of funds, for example, if I want to build a robot at our institute, I need to fund of 35 or 40. Okay, I need to have a manpower. So getting a fund and doing it all the way like challenging. We get a good amount, and I have an opportunity to go to Russia side to have a chat with those professors, and it will really help me to like not just my ideas and to develop prototypes. People looking into their system, own eyes, and thinking of how the things are going on, coming off and trying to search for those like when you don't get a medicine, what do you do? Compositions, right? And you look to the composition and match the composition with something else, right? Similarly, when you go to Russia, when you wait with those prototypes, you try to, okay, you cannot afford this structure because they cost very high. You cannot go for this structure very high. So what things can you do so that I can extract information out of it? For example, using Kalman tree, right? So we determine one state for one sensor, then from those states I can determine other states using Kalman tree. So lots of things have been put for this, not my own idea, different. Like we have a team of 4 to 5 members who contributed really hard to develop this prototype. Still it is at NHRQ. Actually, in fact, we developed 2 prototypes. So, and 2 of them are like one is patent filed, already granted, and on the put. So, one now. In Goa, that's what it is. So in Goa, then we have Bhubaneswar, then NIT Kalkala, then we have one more. Maybe IIT Chennai. Maybe. Trichy. Trichy, no, he started after my guide went into it. I had to go from here started. So after you went, we had a sign with chance government. So wherever Subutha goes, he was trying to go under the vehicle. So that. Thank you, madam, for giving this opportunity to deliver talk. So hopefully, also we should convince you all. I think in academic, we always try to reach out to the audience. Good. So yes, so we'll try that. What I said, if time would have permitted, I could have done the simulation part also. Maybe some stage, perhaps, in the future, and collaborate and work. Thank you. Thank you.
The bonds made by CTTC are never left, sir. We are not going to leave you. Participants are also now part of CTTC team. So they will write to you and should have the patience that why did I get into this? Our people are going to ask you, sir. Looking forward for a lot of collaborative efforts and mutual learning. I would request now Rajan sir to give a moment of our gratitude to you, sir. So when we were looking for speakers for this guest session, we were thinking, let us call one from our teaching fraternity. Then after hunting along, then we found Viranji sir. I and Ritu madam, we were like, "अरे sir, तो यही पर है, हमने तो इतना ढूंढा था." And sir was also very friendly and he also readily accepted us. Thank you very much, sir. for accepting.
Can I have a group photo of the audience? It's a memory for me also, right? That we can have also. Yeah.
All participants have already.
No, sir. I'll share my details. I am from Canada. You know, Deepak, Deepak, now we went to Roorkee University. Oh, yeah, Deepak from Raurkela. Raurkela. He's an head of physics and finally got head also for the second. Right. Water can go up. No, with the pressure. Talking about